In this video, we're going to discuss what's next after we've looked at most of the aspects of a t-test. And we've also looked at confidence intervals, and I'm calling these affectionately our t-tools. And these t-tools are effective methods to make comparisons as long as their requirements are satisfied. One of those requirements is that the sampling was performed randomly and independently selected sample. In Chapter 8, we're going to see what happens when this independent selection is not satisfied, and we'll look at a particular instance of that I've mentioned in a previous video. We'll see what paired data looks like. The other requirement we've discussed is that the individual observations must be independent. If that is not met, there's really not much you can do in the way of a hypothesis test, but you can still use descriptive statistics to describe what is observed in those samples. The last requirement that we've spent the most time on is what I've been calling the normality requirement, just for short, and that is about the corresponding sampling distribution being normally distributed. We can verify this requirement visually by looking at a QQ plot, but we now know of a better method. This was introduced in Lab 8, and that's with the Shapiro normality test. And that is its own little side action hypothesis test where we want a somewhat large enough p-value to assume that that sample came from a normal population. But if that cannot be satisfied, then we have the central limit theorem, which states if you have a sufficiently large sample size, then the sampling distribution will be approximately normal, even if the original population was not. Where we are headed now is addressing what if this normality requirement is not met by these two potential outlets. What could we do? Let's look at some possible solutions, because the potential solution is going to depend on the scenario that you're in or that the data is demonstrating. Well, what if your data was strongly right skewed? We had seen in labs at the beginning of the semester that you could use a transformation such as the natural log to turn severely right skewed data into something that's more bell-shaped. If that's the case, then the way that that manifests into a hypothesis test is you're now no longer talking about the mean of your data, you're talking about the mean of the natural log of your data. And I'm just going to presume that this is happening to both samples that are being compared here. So your inference would be about the mean. Instead of just saying the mean length, it would be the mean of the natural log of your length. So it's not completely free, but your inferences are still going to be about means, but you just have to be careful and mindful about the way that's stated. So a natural log can be used when you have strong skewness, right skewed. Do you remember what we said we could use if your data is slightly right skewed? Recall we said you can use the square root as a more mild transformation. Again, the way this would manifest in your hypothesis, now I'm being brief here, I'm not stating the alternative, but this would manifest as the mean of the square root of your data. And your conclusions would have to be in regards to that transformed data as well. Another instance in which this normality requirement might get violated is with an outlier. Now this one is a bit tricky because one potential solution here is that you would remove the outlier and proceed. But that means you're really modifying your data set. That means a measurement has been taken and it is now, you're removing it kind of willy-nilly. However, if upon inspection you noticed that maybe the entry was entered incorrectly, or there was some error with the instrumentation that was doing the measurement, then that might justify the removal. Caution must be exercised with this option, but there is a possibility to make that work cautiously. Lastly, we do have an alternative test, and it is not a t-test. We're going to discuss the last section in chapter 7, and this is called the Wilcox-Mann-Whitney Test. And to abbreviate that, I will often say Wilcox-Mann-Whitney WMW. But this is another type of hypothesis test. However, it does not have the strict normality requirement that the t-test has. Let's discuss some aspects of this Wilcox-Mann-Whitney test. It is considered a distribution-free test because it does not require that normality requirement like the t-test does. However, it does still require that random and independent sampling was implemented. Additionally, the Wilcox-Mann-Whitney test is what's considered to be a non-parametric test. This is because without a normal distribution, we don't have to focus on the mean, right? The mean is a parameter best applied to normal distributions. So this Wilcox-Mann-Whitney test does not focus on a parameter like the mean. When we formulate a hypothesis for the Wilcox-Mann-Whitney test, that hypothesis is not in regards to the mean, but is in regards to the general distribution of your variable. So not the mean of the variable, but its general distribution. I've got the book open here so we can look at some examples of the Wilcox-Mann-Whitney test in the textbook. This is in chapter 7.10, page 282. And I'm going to skip past this first block because I've already discussed that. Let's look at this first example about soil respiration, which is a measure of microbial activity in soil,
which affects plant growth. Certainly, in one study, the soil cores were taken from 2 locations in a forest, under the opening in the forest canopy, a gap location, and at a nearby area under heavy tree growth, the growth location. And they were looking at the carbon dioxide given off by each of the soil cores that were measured.
If the data passed the requirements for a t-test, then we would mention that the mean carbon dioxide levels are the same in the gap and the growth locations. But because this is a Wilcox-Mann-Whitney example, there is no mention of the mean here. Here, they are saying that the populations from which the two samples were drawn have the same distribution of soil respiration. As mentioned, the Wilcox-Mann-Whitney test does not mention the mean. They have other examples I will scroll down to here. They've got the data there. Another way to state the null hypothesis would be that the gap and growth areas do not differ with respect to soil respiration. A non-directional alternative could be stated as such. The distribution of soil respiration tends to be higher in one of the two populations. They might know which one. It might be the gap or the growth group. So these alternative and null hypotheses will be stated in a brief sentence. There's not really a nice notationally compact way to state these, which I think most people kind of like. Let's scroll down to some of the imagery they have here. They have plotted on the same axis the measurements from the growth and the gap area. It sure looks like there is a difference between those. And if you continue on, it does appear that these QQ plots are not showing normality. And as you can see, they do not have sufficiently large sample sizes. If we want to make a comparison between these two samples, they are candidates for the Wilcox-Mann-Whitney test. The methodology for this, we will not describe in detail. I welcome and invite you to dive into this in the book. However, it's a little tough to explain over video, but the dedicated individual can certainly make up and down of this where it's written in the textbook. Instead, the approach that I would like to take is I'm going to show you how to do this in R. I'm going to scroll back up to the raw data here and show you that I have transcribed that into R. I have made two vectors. I've got my gap values and I've got the values identified from the heavy overgrown canopy. I have retranscribed the hypotheses written in the book here just so we don't have to switch screens back and forth, and I have input the data in. To do the Wilcox test, it is Wilcox.test, and I would enter the two vectors of data. Now I typed these in manually, so I don't need to use the $ symbol. Usually when we upload data from Canvas, it uploads as a data frame in which you would have to do something like, data, $, blah, blah, blah. So I don't need to do that here because I've defined these precisely. I need to input one more thing into the Wilcox.test here. Do you see what it is? I need to specify this alternative hypothesis, which is directional. So that is with the code alt equals, now let's think, should I write less or should I write greater in the text I'm about to type? Their alternative hypothesis, they think that the growth region will have greater carbon dioxide respiration, greater in the growth. But I typed gap first, so I should write less. If I wanted to write the word greater there, I could, if I had just input my vectors in the opposing manner. If I had done growth, comma, gap, now I can write greater into that alternative hypothesis. So these two should get you the same output. There is the output for the Wilcox-Mann-Whitney test. There's a warning message here. Based on the methodology of the Wilcox test, there is a potential for warning messages. We're just going to disregard them. At the end of the day, we're going to look at this p-value. And it's pretty small, right? 0.007. Ooh. Just for fun, I want to run this other Wilcox.test command just to show you that we would get the same p-value. Okay, so here I did the less than version, 0.007, and here I did the greater than version with the reverse arrangement of the data input, and I still got 0.007. The conclusion, therefore, would be to reject the null hypothesis. Now, we didn't discuss our level of significance, but this p-value is less than any reasonable alpha, but remember, without any specification for alpha, we'll use 0.05. So that's our conclusion. If we were to state that in the context of the problem mentioning the study variables, I would say that the data provides evidence to support the alternative hypothesis, and since it's already typed, I'm just going to be a little lazy and copy paste that. So I hope this was useful for you. The Wilcox-Mann-Whitney test can be used when we do not meet the t-test requirements. And we will do a lot more examples of this in Lab 9, where we will compare and contrast how the t-test performs alongside the Wilcox-Mann-Whitney test in various conditions.